Welcome to Methods in Biostatistics. Today, we are diving into two of the most fascinating and crucial concepts in data analysis: skewness and kurtosis. When we collect biological data, we often hope it forms a perfect, symmetrical bell curve. But nature is rarely that perfect. Understanding how and why our data deviates from this ideal shape is essential for making accurate medical and biological predictions. Let us begin our journey into the shapes of data. Now that we have introduced our topic, let us look at what skewness actually means. Imagine looking at a perfectly symmetrical mountain. In statistics, this represents a normal distribution, where data gathers evenly around the center. However, in biology and medicine, data rarely forms this perfect mountain. Sometimes the mountain leans heavily to one side. This leaning or lack of symmetry is what we call skewness. It tells us if our data is balanced or if it is being pulled in one specific direction by unusual, extreme values. Recognizing this is critical because applying standard tests to skewed data can lead to completely invalid and misleading results. Building on the idea of asymmetry, let us explore the two directions data can lean. If a distribution is perfectly symmetrical, its skewness is exactly zero, meaning the mean, median, and mode all fall at the exact same central point. But when data has a positive skew, or is right-skewed, it means there is a long tail extending towards the higher numbers on the right side. A great example is the incubation period of a disease, where most get sick quickly, but a few take weeks. Conversely, a negative skew, or left-skewed distribution, has a long tail stretching towards the lower numbers on the left. In these skewed distributions, the mean is always pulled in the direction of that long tail. Having understood the concept of skewness, let us look at how we mathematically measure it. This formula calculates the sample skewness, which quantifies the exact asymmetry of our dataset. The numerator represents the third central moment. Notice that we cube the distance of each data point from the mean. Cubing is incredibly important here because it preserves the negative or positive sign of that distance, which tells us the direction the data leans. The denominator is the standard deviation cubed. We divide by this to standardize our measurement, allowing us to compare skewness across completely different biological datasets, regardless of whether we are measuring days, milligrams, or heartbeats. If the final value is greater than 0, the data is right-skewed. While the previous formula is precise, calculating third moments by hand can be tedious, which brings us to a simpler, very common practical formula. This is Pearson's second coefficient of skewness. Instead of complex summations, it uses three basic descriptive statistics: the mean, the median, and the standard deviation. Conceptually, it relies on the fact that in a skewed distribution, the mean is pulled away from the median, towards the tail. By subtracting the median from the mean, we immediately see the direction of the skew. We multiply by 3 as a scaling factor, and then divide by the standard deviation, S, to standardize the result. If the mean is higher than the median, the result is positive, indicating a right skew. Now that we have our formula, let us see this with a concrete example. We are studying the recovery time in days for 5 patients. The times are 2, 3, 4, 5, and 16 days. We want to determine if this data is skewed. First, we calculate the mean by adding the values and dividing by 5, giving us 6 days. The median, our middle value, is 4 days. Notice the mean is already larger than the median. Next, we calculate the standard deviation, which comes out to approximately 5.18 days. Finally, we plug these into Pearson's formula. 3 times the difference of 6 and 4 divided by 5.18. Our final answer is 1.16. Physically, this positive number confirms our data is right skewed, pulled by that one unusually long 16-day recovery. To truly grasp what our calculation means, let us visualize this right-skewed distribution. Here, you are looking at a frequency curve that perfectly represents our patient recovery data. The horizontal axis shows the data values, and the vertical axis shows the frequency. Notice the shape. The peak is concentrated on the left, representing the majority of patients who recovered quickly. But look at that long tail stretching far out to the right. That tail is caused by our extreme 16-day recovery time. Crucially, look at the 3 dashed lines. The mode is at the highest peak. The median is slightly to the right, and the mean is pulled furthest to the right, deep into the tail. This visual perfectly illustrates why the mean is greater than the median in a positively skewed dataset. Having mastered skewness, this brings us to our second major concept, kurtosis. Imagine you are looking at 3 different tents set up in a field. One is a standard tamping tent, one is a very tall, sharp teepee, and the third is a wide, flat dome. If these tents represent data distributions, they might all have the exact same mean and perfect symmetry, but they look completely different vertically. This difference in vertical shape and the thickness of their edges is kurtosis. Kurtosis is the measure of tailedness, or the extremity of outliers in a probability distribution. It tells us if our data is heavily concentrated in the center with thick, heavy tails, or spread out with very thin, light tails. This is vital because in biology, tails represent extreme events, which can sometimes be a matter of life and death. Now that we know kurtosis measures tailedness, let us categorize the different shapes a distribution can take. Modern statisticians emphasize that kurtosis primarily measures how much data is located in the tails compared to the center. We use a normal distribution as our baseline standard, which is called mesokurtic. If a distribution has a sharp peak and fat, heavy tails, it is called leptokurtic. A leptokurtic distribution has more extreme outliers than a normal distribution. On the other hand, a distribution with a flatter peak and thin, light tails is called platykurtic. This means it has fewer outliers and the data is more uniformly spread. If a researcher assumes biological data is mesokurtic when it is actually leptokurtic, they will severely underestimate the risk of extreme, potentially fatal medical events. To quantify these tail weights, let us look at the mathematical formula for kurtosis. Conceptually, this formula is very similar to skewness, but instead of the third moment, we use the fourth central moment. In the numerator, we raise the distance of each data point from the mean to the power of 4. Raising to the 4th power acts like a massive magnifying glass for outliers. Numbers far from the mean become absolutely huge, which is exactly why kurtosis is so incredibly sensitive to the tails of the distribution. We then divide by the standard deviation raised to the 4th power to standardize the value. A perfect normal distribution has a kurtosis of exactly 3. Because of this, statisticians often use excess kurtosis, which is simply k minus 3, setting the baseline for a normal distribution to exactly 0. Before we move on, let us see this with a concrete example in genetics. We are studying gene mutations in 2 fruit fly populations. We are given that population A has an excess kurtosis of 2.5 and population B has an excess kurtosis of -1.2. We need to interpret what this means for predictability. For population A, the excess kurtosis is greater than 0, classifying it as leptokurtic. This means it has fat tails, so we can expect a surprisingly high number of flies with an extreme number of mutations. It is highly unpredictable. For population B, the excess kurtosis is less than 0, classifying it as platykurtic. This means it has thin tails. Extreme mutation events are very rare here, making the genetic outcomes in population B much more predictable and stable. To solidify our understanding of these classifications, let us look at them side by side. In this diagram, you are seeing all 3 types of kurtosis centered on the same mean. The horizontal axis represents our data values, and the vertical axis is frequency. Look at the blue curve in the middle. This is our mesocuric, normal baseline. Now look at the red curve. This is the leptokurtic distribution. Notice how its peak is much sharper, but more importantly, look at its tails. They are noticeably thicker and higher than the blue curve, representing those extreme outliers. Finally, observe the green curve, the platykurtic distribution. Its peak is lower and flatter, and its tails are very thin, hugging the axis closely, showing that extreme values are highly unlikely. This visual perfectly summarizes how kurtosis shapes our data. We have covered a lot of ground today, so let us summarize our key takeaways. First, skewness is your tool for detecting asymmetry. It tells you if your data leans to the left or the right, pulling the mean away from the median. Second, kurtosis measures the tailedness of your distribution. It warns you if your data is prone to extreme, rare events, which is critical in biological contexts. A leptokurtic distribution means expect the unexpected, while a platykurtic one assures stability. Together, these 2 measures provide a complete, detailed picture of your data's shape, going far beyond just the average and the spread. Always check these before assuming your biological data is perfectly normal. You now have the tools to truly understand the shape of your data.